Imagine accelerating toward the speed of light in a spacecraft. Your watch ticks normally, your heart beats at its usual rhythm. But back on Earth, something extraordinary is happening. For every year you experience, decades are passing at home. Push closer to light speed, and the effect becomes extreme. At 99.9% light speed, your day becomes 2 months on Earth. But what happens if you actually hit light speed? Does time stop completely? If you're fascinated by these mind-bending mysteries of physics, make sure to subscribe to this channel and give a thumbs up. And one quick question: if you could change one thing about the universe, what would it be? Let me know in the comments down below. I will choose the most creative answer. Now let's begin. To understand what happens to time at the speed of light, we need to start with one of the most profound discoveries in human history. Time is not absolute. Before Einstein, everyone believed time was like a universal clock ticking the same for everyone, everywhere. Newton built his entire physics on this assumption, but in 1905, a 26-year-old patent clerk in Switzerland shattered this comfortable illusion forever. Einstein's special theory of relativity revealed that time is personal. Every observer carries their own clock, and these clocks can tick at different rates depending on how fast they're moving. This isn't science fiction or theoretical abstraction, it's measurable, observable reality that affects everything from the GPS in your phone to the particles raining down from space. The story begins with light itself. In the late 1800s, physicists discovered something troubling. Maxwell's equations showed that light travels at a specific speed, about 300,000 kilometers per second in vacuum, but speed relative to what? When you throw a ball from a moving train, its speed adds to the train's speed, but experiments showed light doesn't follow this rule. Whether you're moving toward a light source or away from it, you always measure the same speed of light. The Michelson-Morley experiment in 1887 tried to detect Earth's motion through the supposed ether that carried light waves. They found nothing. Light moved at the same speed in all directions, regardless of Earth's motion through space. This null result created a crisis in physics that only Einstein could resolve. His solution was radical: accept that light speed is constant for all observers and let everything else adjust. If light speed must remain constant, then space and time themselves must be flexible. This leads directly to time dilation, the slowing of time for objects in motion. The mathematics is beautifully simple, yet profoundly strange. The time dilation factor, called gamma, equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. When you're standing still, gamma equals 1, no time dilation. But as velocity increases, gamma grows larger, meaning time passes more slowly for the moving observer. At 10% light speed, time slows by just 0.5%, barely noticeable. At 50% light speed, time runs about 13% slower. At 90% light speed, time passes less than half as fast. At 99% light speed, time slows by a factor of 7. And as you approach 100% light speed, something extraordinary happens. Gamma approaches infinity. This is where our journey gets truly mind-bending. As you get closer and closer to light speed, time dilation becomes more and more extreme. At 99.9% light speed, time slows by a factor of 22. At 99.99%, it's 71. Add more nines, and the factor grows without limit. At exactly light speed, the equation breaks. Gamma becomes infinite, suggesting time stops entirely. But here's the crucial point that often gets misunderstood. From your perspective inside the speeding spacecraft, time flows normally. Your watch ticks at 1 second per second. Your thoughts flow at normal speed. Your heart beats its usual 70 times per minute. The time dilation is only apparent to outside observers watching you zoom past. This reciprocal nature of time dilation seems paradoxical. If you see Earth's clocks running slow as you speed away, and Earth sees your clocks running slow, who's right? The answer is both and neither. In special relativity, there's no absolute reference frame. Motion is relative, and so is time dilation. So is... The asymmetry only appears when someone changes reference frames. Accelerating or decelerating breaks the symmetry. Real experiments have confirmed these predictions with stunning accuracy. In 1971, physicists Hafele and Keating flew atomic clocks around the world on commercial airliners. When compared to reference clocks on the ground, the flying clocks showed the predicted time dilation. They had aged slightly less than the stationary clocks. The difference was tiny, mere nanoseconds, but measurable and exactly what Einstein predicted. Particle accelerators provide even more dramatic confirmations. At CERN's Large Hadron Collider, protons are accelerated to 99.99999% light speed. At this velocity, time dilation is so extreme that unstable particles that should decay in microseconds survive for much longer, from our perspective, traveling meters instead of millimeters before decaying. Cosmic ray moons offer a natural demonstration. These particles are created when cosmic rays strike the upper atmosphere, about 15 kilometers up. Moons have a half-life of just 2.2 microseconds. They shouldn't survive the journey to Earth's surface, even at near light speed. Yet we detect them in abundance at sea level. Why? Time dilation. From our perspective, their clocks run slow, giving them time to reach the ground. From the muon's perspective, length contraction makes the atmosphere thinner, reducing the distance they need to travel. GPS satellites must account for time dilation to maintain accuracy. These satellites orbit at about 14,000 kilometers per hour, fast enough that special relativistic time dilation slows their clocks by about 7 microseconds per day. Combined with gravitational time dilation effects, GPS clocks must be corrected by 38 microseconds daily. Without these relativistic corrections, GPS would accumulate errors of over 11 kilometers per day. But what about photons? Particles of light that actually do travel at light speed? This is where things get philosophically profound. According to special relativity, photons experience no time at all. From a photon's perspective, emission and absorption happen simultaneously, regardless of the distance traveled. A photon emitted by a star in Andromeda Galaxy, traveling for 2.5 million years from our perspective, experiences its entire journey in zero time. This brings us to one of the most profound mysteries in physics. What is the universe like from a photon's point of view? If time truly stops at light speed, then every photon exists in an eternal now, a timeless state where its entire journey from creation to absorption happens instantaneously. This isn't just philosophical speculation, it's a direct consequence of Einstein's equations that challenges our deepest assumptions about consciousness, existence, and the nature of reality itself. Think about the light entering your eyes right now. Some of it came from your screen, traveling for mere nanoseconds. But the ambient light bouncing around your room might include photons that have been journeying for billions of years. That sunlight streaming through your window left the sun's surface 8 minutes ago, but the energy it carries was generated in the solar core hundreds of thousands of years earlier, slowly working its way to the surface. From our perspective, these photons have vastly different ages and histories, but from the photon's perspective, if such a thing even makes sense, all journeys are identical, zero duration. A photon traveling from the Big Bang to your eye experiences no time whatsoever. In its reference frame, the universe has zero thickness in the direction of travel, and its entire existence is compressed into a single, timeless moment. This raises profound questions about the nature of experience and consciousness. Can something that experiences no time be said to exist in any meaningful way? If you're intrigued by these deep connections between physics, consciousness, and the nature of time, I recommend the book called Transcending the Speed of Light: Consciousness, Quantum Physics, and the Fifth Dimension by Mark Cypher. While it ventures into speculative territory beyond mainstream physics, it explores fascinating questions about whether consciousness itself might transcend the ordinary speed limits of spacetime. It's thought-provoking reading for anyone pondering the deeper mysteries we're discussing. The link is in the description and pinned on the comments. Now let's return to what mainstream physics tells us about time at light speed. The impossibility of reaching light speed for massive objects isn't just a practical limitation, it's built into the fabric of spacetime. As we've seen, the time dilation factor approaches infinity as velocity approaches light speed. This means it would take infinite energy to accelerate any mass to light speed. The universe has built-in protection against massive objects reaching this ultimate speed limit. But why is this limit exactly what it is? Why 300,000 kilometers per second and not some other value? The answer lies deeper than you might expect. Light speed isn't really about light. It's the fundamental rate at which cause and effect can propagate through spacetime. It's the speed of causality itself, the maximum rate at which information can travel. Light just happens to travel at this speed because photons are massless. The value of light speed emerges from two fundamental properties of empty space: the electric permittivity and magnetic permeability of vacuum. These aren't arbitrary numbers, but seem to be woven into the structure of spacetime itself. In a very real sense, light speed is the conversion factor between space and time, telling us how to translate between the two in our four-dimensional universe. Recent experiments have pushed our understanding of time dilation to new extremes. The ALPHA experiment at CERN has trapped antihydrogen atoms and studied their properties. While these antimatter atoms move slowly compared to light speed, the precision of modern measurements allows scientists to test whether antimatter experiences time dilation identically to matter. So far, it does. Gravitational wave detectors like LIGO and Virgo have observed black hole mergers, where the objects spiral together at significant fractions of light speed in their final moments. The gravitational waves themselves propagate at exactly light speed, confirming that gravity's influence travels at the same cosmic speed limit as electromagnetic waves. When two black holes merge, the final orbits see them moving at over half light speed, experiencing extreme time dilation that's encoded in the gravitational wave signal. The twin paradox remains one of the most discussed aspects of relativistic time dilation. One twin stays on Earth while the other travels to a distant star at near light speed. When the traveling twin returns, they've aged less than their Earth-bound sibling. This isn't a paradox once you understand that the traveling twin changed reference frames during their journey. They accelerated, turned around, and decelerated, breaking the symmetry between the twins. Real-world examples of differential aging exist all around us. Astronauts on the International Space Station age slightly slower than people on Earth due to their orbital velocity. Scott Kelly spent 340 days in space while his identical twin Mark stayed on Earth. Scott aged about 5 milliseconds less than Mark, a tiny but real effect of time dilation. But let's push further toward light speed. At 99.999% light speed, time dilation becomes so extreme that a journey to the center of our galaxy, 26,000 light-years away, would take just 52 years from the traveler's perspective. The entire observable universe could be crossed in a human lifetime if we could somehow approach light speed closely enough. This creates a strange situation. The universe becomes traversable for the traveler, but at a terrible cost. Everyone and everything they knew on Earth would be long dead upon their return. Time dilation doesn't let you travel into the past, but it does let you travel into the future, a one-way journey from which there's no return to your original time. Quantum mechanics adds another layer of mystery to our story. While special relativity deals with the macroscopic world, quantum field theory describes particles and forces at the smallest scales. In this framework, virtual particles constantly pop into existence and annihilate, borrowing energy from the vacuum for times so brief they don't violate conservation laws. Do these virtual particles experience time? If they travel at light speed during their brief existence, are they timeless like photons? The Unruh effect predicts that accelerating observers see empty space filled with a warm bath of particles. From the perspective of an accelerating observer approaching light speed, the vacuum itself would appear to heat up, eventually reaching infinite temperature at light speed. This suggests that the approach to light speed isn't just difficult, it's accompanied by increasingly exotic physical phenomena. String theory and other attempts at quantum gravity suggest that space-time itself might break down at the smallest scales. The Planck time, about 10 to the negative 43 seconds, might represent the smallest meaningful unit of time. If so, then the smooth time dilation we calculate might become granular at extreme speeds, though this regime is far beyond current experimental reach. Recent proposals for detecting high-energy cosmic neutrinos rely on understanding time dilation at extreme energies. The IceCube detector in Antarctica has observed neutrinos with energies suggesting they're traveling at 99.999999% light speed or faster. At these speeds, time dilation is so extreme that the neutrinos experience mere seconds while traversing billions of light-years from our perspective. To truly understand what happens to time at light speed, we need to think geometrically. Einstein's teacher, Hermann Minkowski, showed that special relativity is best understood by combining space and time into a four-dimensional spacetime. In this geometric view, the mystery of time dilation becomes as clear as understanding why a tilted ladder appears shorter when viewed from the side. What we call time dilation is actually a rotation in four-dimensional spacetime. Imagine spacetime as a vast four-dimensional fabric where every event, from the birth of a star to your heartbeat right now, has coordinates in both space and time. You're not just located somewhere, you're located somewhere. Your entire life traces a path through this four-dimensional space called a world line. And here's the key insight. Everyone's world line has the same four-dimensional length between birth and death, but that length can be distributed differently between space and time. Think of it like this. You're always moving through space-time at exactly the speed of light. When you're sitting still in space, all your motion is through time. You're traveling into the future at maximum speed, 1 second per second. But when you move through space, some of that motion gets redirected. The faster you move through space, the slower you move through time. At light speed, all your motion would be through space with none left for time. This geometric view explains why nothing can exceed light speed. You can't go faster through space-time than you're already going. Light speed is your total, constant velocity through the four dimensions. Asking why we can't go faster than light is like asking why we can't go north of the North Pole. The geometry simply doesn't allow it. The mathematics of this four-dimensional rotation is encoded in the Lorentz transformation. Just as rotating an object in 3 dimensions mixes its length, width, and height components, moving through space-time mixes space and time coordinates. The mixing follows hyperbolic functions rather than the circular functions of ordinary rotation, which is why space-time geometry is called hyperbolic or Minkowskian rather than Euclidean. This geometric understanding reveals something profound about simultaneity. In Newton's universe, everyone agreed on what now meant across the cosmos. But in Einstein's universe, simultaneity is relative. Events that are simultaneous for one observer happen at different times, for another observer moving at a different velocity. There is no universal now slicing through space-time. Each observer cuts their own slices at different angles. Consider a thought experiment. You're on a train platform as a high-speed train passes. Lightning strikes both ends of the train simultaneously in your reference frame. But for someone on the train, the lightning strikes aren't simultaneous. The strike at the front of the train happens first. Neither perspective is wrong. Simultaneity simply isn't absolute. This relativity of simultaneity becomes extreme as speeds approach light speed. The light cone structure of spacetime provides the ultimate framework for understanding causality and time's behavior. At every point in spacetime, imagine two cones touching at their tips. The future light cone contains all events that this point can influence. The past light cone contains all events that could have influenced this point. Everything else is in the elsewhere. Events that cannot be causally connected without faster-than-light travel. For massive objects, world lines must always stay within the light cones, moving from past to future. But photons travel along the light cones themselves, on the boundary between time-like and space-like separation. This boundary existence is why photons experience no time. They're always on the edge between cause and effect, between past and future. Recent experiments with quantum optics have probed the nature of time for photons in unprecedented ways. Researchers at the University of Vienna have created elaborate setups where single photons travel through interferometers with path lengths differing by many meters. Despite these different paths, the photon interferes with itself, suggesting it somehow experiences all paths simultaneously in its timeless journey. The Wheeler-Feynman absorber theory proposed an even stranger view. Photons might experience their entire journey from emission to absorption as a single event, with the future absorption affecting the past emission. While this interpretation remains controversial, it highlights how deeply mysterious the photon's timeless perspective remains. Wormholes, if they exist, would represent another regime where normal concepts of time break down. These hypothetical shortcuts through spacetime could connect distant regions, potentially allowing apparent faster-than-light travel. But the physics of wormholes requires exotic matter with negative energy density, and any attempt to use them for time travel seems to generate paradoxes that physics abhors. The Alcubierre drive represents a theoretical way to achieve apparent faster-than-light travel without locally exceeding light speed. By contracting space in front and expanding it behind, a spacecraft could surf a wave of warped space-time. Inside the warp bubble, time would flow normally, but the bubble itself could traverse vast distances. However, the energy requirements and causality problems make this remain firmly in the realm of speculation. Tachyons, hypothetical particles that always travel faster than light, would experience time in reverse from certain reference frames. If they existed, they would challenge our understanding of causality and create grandfather paradox scenarios. The fact that we've never observed tachyons despite decades of searching suggests the universe really does enforce its speed limit strictly. The cosmic speed limit creates what physicists call the chronology protection conjecture. Proposed by Stephen Hawking, it suggests that the laws of physics conspire to prevent time travel paradoxes. Whenever conditions might allow closed time-like curves, paths through space-time that loop back to their own past, quantum effects or other phenomena intervene to prevent them. Black holes provide natural laboratories for extreme time dilation. As you approach the event horizon, gravitational time dilation compounds with special relativistic effects. From the perspective of distant observers, time appears to stop at the horizon. You would never be seen crossing it. Your final moments would appear frozen forever. Yet from your perspective, you'd pass through the horizon in finite time, experiencing the interior of the black hole that outside observers can never witness. The information paradox at black hole horizons connects time dilation to fundamental questions about quantum mechanics. If information falling into a black hole appears frozen at the horizon from outside perspectives, but the black hole eventually evaporates through Hawking radiation, what happens to that information? This puzzle has driven decades of research into quantum gravity. Cosmic inflation in the early universe represents a regime where the usual rules about light speed and time were transcended. During inflation, space itself expanded faster than light, carrying regions apart at superluminal speeds. This wasn't motion through space, but expansion of space itself. Time during inflation becomes a complex concept, with different regions experiencing drastically different rates of time flow. Let's take an imaginary journey toward light speed and experience firsthand how time gradually grinds to a halt. Imagine you're in a spacecraft with unlimited fuel and perfect engines. As you accelerate, the universe around you begins to transform in ways that defy everyday experience. This isn't just about time slowing down, it's about reality itself warping into something unrecognizable. At first, the effects are subtle. Accelerating to 1% light speed, 3,000 kilometers per second, you'd hardly notice any difference. Time dilation is just 0.005%. Your twin back on Earth ages 1 hour and 3 seconds for every hour you experience. The stars ahead shift slightly blue, while those behind shift red, but otherwise, space looks normal. Push to 10% light speed, and things get interesting. Time dilation reaches 0.5%. A year for you is a year and 5 days on Earth. The Doppler effect becomes noticeable. Stars ahead glow bluer and brighter, while those behind redden and dim. But the real surprise is aberration. Stars appear to crowd toward your direction of travel, as if the universe is funneling into a point ahead of you. At 50% light speed, the effects are unmistakable. Time dilation hits 15%. Your decade-long journey sees Earth age 11.5 years. The forward view concentrates into an ever-brightening circle of blue-shifted stars. Behind you, a growing circle of darkness expands as red-shifted stars fade beyond visible wavelengths. You're entering a tunnel of light. 90% light speed transforms everything. Time dilation factor, 2.3. A year for you is over 2 years on Earth. The entire visible universe compresses into a blazing ring of light ahead of you, the searchlight effect of special relativity. Stars directly ahead, blue shift into the X-ray spectrum, while the cosmic microwave background radiation ahead blue shifts into visible light. You're seeing the birth of the universe in real time. At 99% light speed, the universe becomes alien. Time dilation factor, 7. Your subjective year spans 7 Earth years. The ring of light ahead intensifies beyond description. Particle collisions with interstellar hydrogen, normally harmless, now strike with the energy of rifle bullets. Your spacecraft needs shielding that could stop a nuclear blast just to survive the interstellar medium. Push to 99.9% and you enter a realm of physics extreme. Time dilation factor, 22. A month for you is nearly 2 years on Earth. The energy required to maintain acceleration against relativistic mass increase is staggering. Each proton of interstellar hydrogen hits like a cosmic ray. The universe ahead compresses into a blindingly bright point while everywhere else is darkness. But here's where our journey must end, because the universe itself forbids further progress. The energy needed to accelerate increases without bound. At 99.99% light speed, pushing a single kilogram faster requires the energy output of a large power plant. At 99.999%, you'd need to convert entire planets to energy. The universe becomes an impenetrable wall of infinite energy requirements. This isn't just about running out of fuel. As physicist E.F. Taylor put it, space itself resists your acceleration. The Higgs field, which gives particles mass, becomes like cosmic molasses at extreme speeds. Virtual particles in the quantum vacuum create a kind of friction. The universe uses every mechanism at its disposal to enforce its speed limit. The Large Hadron Collider demonstrates these limits daily. Despite using enough power to light a small city, it can only push protons to 99.99999% light speed, still short of true light speed by 7 meters per second. Each additional 9 in that percentage requires roughly 10 times more energy than the last. Perfect light speed would require infinite energy. But what if we could somehow borrow that infinite energy? What if we could ride a beam of light itself? Here we enter the realm of photon consciousness, a philosophical puzzle that has haunted physics since Einstein. From a photon's perspective, if such exists, the universe has zero extent in its direction of travel due to infinite length contraction. All of space compresses to a two-dimensional sheet with zero thickness. More bizarre still, from the photon's view, emission and absorption are simultaneous. A photon emitted by a star in Andromeda and absorbed by your retina 2.5 million years later experiences its entire journey instantaneously. It exists in a timeless, spaceless state that challenges our very concepts of existence and experience. This leads to profound questions about the nature of reality. If photons experience no time, do they experience anything at all? Can something exist without duration? The photon's perspective suggests a block universe where past, present, and future coexist eternally, with time being an illusion created by our limited perspective as we trace our world lines through spacetime. Recent neutrino experiments add another piece to this puzzle. Neutrinos have tiny but non-zero mass, meaning they travel just below light speed. The Opera experiment in 2011 initially reported neutrinos traveling faster than light, creating a sensation. But careful rechecking revealed measurement errors. Even neutrinos, with masses millions of times smaller than electrons, cannot break the cosmic speed limit. The IceCube Neutrino Observatory in Antarctica detects neutrinos with energies so high they're traveling at 99.999999% light speed or more. Yet even these cosmic bullets, accelerated by the most powerful phenomena in the universe, fall infinitesimally short of true light speed. Time passes for them, however, slowly. A billion years might feel like minutes. Cosmic rays provide natural experiments in extreme time dilation. The Oh My God particle, detected in 1991, was a proton with energy equivalent to a baseball pitched at 60 miles per hour. It was traveling so close to light speed that crossing our galaxy would take just minutes from its perspective. Yet it still experienced time, still fell short of the photon's timeless state. The GZK cutoff demonstrates how extreme time dilation affects particle physics. Protons with energies above 5 times 10 to the 19 electron volts should interact with cosmic microwave background photons, creating pions and losing energy. From our perspective, this limits how far ultra-high-energy cosmic rays can travel. But from the proton's perspective, the CMB is blue-shifted to gamma rays, creating a wall of radiation that degrades its energy. As we push deeper into the mysteries of time at light speed, we encounter paradoxes that have puzzled physicists for over a century. These aren't just mathematical curiosities. They reveal fundamental truths about the nature of time, causality, and existence itself. Each paradox we resolve deepens our understanding, but also opens new questions about what it means for time to stop. The most famous is the twin paradox, which seems to create a logical contradiction. If motion is relative, why does only one twin age less? The resolution lies in the asymmetry of their journeys. The traveling twin changes reference frames, accelerating, turning around, and decelerating. These accelerations break the symmetry, creating an absolute difference in their paths through spacetime. The traveling twin's world line through four-dimensional spacetime is genuinely shorter, resulting in less elapsed proper time. But what happens if we push the twin paradox to its extreme? Imagine the traveling twin accelerates ever closer to light speed. From Earth's perspective, their journey takes longer and longer, but they age less and less. At the limit of light speed, the paradox reaches its ultimate form. The journey takes infinite time from Earth's view, but zero time from the traveler's view. This mathematical singularity hints at why massive objects cannot actually reach light speed. The relativity of simultaneity creates even stranger scenarios. Imagine a spacecraft traveling at near light speed past Earth just as two supernovae explode, one ahead and one behind Earth's position. From Earth's perspective, they explode simultaneously. But from the spacecraft's view, the forward supernova explodes first. Now at a second spacecraft traveling in the opposite direction, it sees the rear supernova explode first. Three observers, three different orderings of events. As we approach light speed, these differences become extreme, challenging our notion of a universal now. If you're fascinated by these time dilation effects and want to understand the physics more deeply, check out my video called Time Dilation: Why Moving Faster Slows You Down. I break down the mathematics and show real-world examples of how motion through space affects your journey through time, from GPS satellites to particle accelerators. It's the perfect companion to understand why approaching light speed makes these effects so extreme. The link is in the description and on the card above. Now let's explore what happens when we push these concepts to their absolute limits. The searchlight paradox illuminates another puzzle. Imagine a lighthouse whose beam sweeps across the sky. At sufficient distance, the spot of light on clouds moves faster than light speed. Does this violate relativity? No, because the spot isn't a physical object, it's a projection. No information or energy actually travels faster than light. But this paradox helps us understand why reaching light speed is impossible. It would require coordinating events across space faster than causality allows. Quantum mechanics adds new layers of paradox. The quantum Zeno effect shows that frequent observation can freeze a quantum system's evolution. If time stops at light speed, would quantum systems be perpetually frozen? Would superposition collapse? The intersection of quantum mechanics and relativistic time dilation remains one of physics' deepest mysteries. Recent experiments with time crystals, structures that repeat in time rather than space, challenge our understanding of time's flow. These quantum systems exhibit periodic behavior without energy input, seeming to violate thermodynamics. While they don't actually break physics laws, they suggest time might be more flexible than classical relativity suggests, especially at quantum scales approaching light speed. The information paradox becomes acute at light speed. Information cannot travel faster than light. This is fundamental to causality. But if time stops at light speed, how can information be processed? A computer traveling at light speed would be frozen, unable to complete calculations. This suggests that consciousness, computation, and information processing are fundamentally incompatible with light-speed travel. Consider the photon's journey from distant galaxies. Some photons we detect today have been traveling for over 13 billion years, carrying information about the early universe. From our perspective, they're ancient messengers. But from the photon's perspective, emission and detection are simultaneous. How can something convey information about the past if it experiences no time? This paradox touches on deep questions about the nature of information itself. The expansion of space adds another paradox. Galaxies can recede from us faster than light due to cosmic expansion. Space itself stretches, carrying galaxies apart. From our perspective, time dilation should affect these galaxies. But the expansion of space isn't motion through space, so special relativistic time dilation doesn't apply. Instead, cosmological time dilation stretches the duration of events we observe in distant galaxies. Black holes create the ultimate time paradox. As matter approaches the event horizon, gravitational time dilation approaches infinity. From outside, we never see anything cross the horizon. Time freezes at the boundary. Yet from the falling object's perspective, crossing happens in finite time. This paradox connects to the black hole information problem and suggests that time's nature changes fundamentally in extreme gravity. The tachyon paradox explores what would happen if something could travel faster than light. Such particles would move backward in time from some reference frames, enabling grandfather paradoxes where effects precede causes. The universe seems to forbid tachyons, maintaining causality by enforcing the light speed limit. Every search for tachyons has failed, suggesting the universe really does protect its causal structure. Wormholes, if they exist, would create closed, time-like curves, paths through space-time that loop back to their own past. But quantum effects seem to destabilize any wormhole that could create paradoxes. The universe appears to have what Hawking called a chronology protection agency, preventing paradoxical situations. Light speed isn't just a speed limit, it's a guardian of logical consistency. The EPR paradox and quantum entanglement seem to violate light speed limits. Entangled particles correlate instantaneously regardless of separation. But careful analysis shows no information travels faster than light. The correlations are real but can't be used for communication. This suggests that the universe allows instantaneous correlations while still protecting causality, a subtle distinction that took decades to understand. Recent experiments with quantum teleportation have pushed these boundaries further. While the quantum state of a particle can be teleported to a distant location, the process requires classical communication limited by light speed. The universe seems carefully designed to allow quantum weirdness while preventing faster-than-light information transfer. Every claim about time stopping at light speed must face the ultimate test, experimental verification. From particle accelerators that push matter to within a whisper of light speed to cosmic observations of the most energetic events in the universe, nature provides countless experiments that reveal how time behaves at extreme velocities. These aren't thought experiments or mathematical abstractions, they're real measurements that confirm, refine, and sometimes surprise our theoretical understanding. The most direct evidence comes from particle accelerators. At Fermilab's Tevatron, which operated until 2011, protons were accelerated to 99.9995% light speed. At these velocities, time dilation factor exceeded 1000. Unstable particles that should decay in nanoseconds survived for microseconds from our perspective, traveling hundreds of meters instead of fractions of a millimeter. Every decay curve matched relativistic predictions perfectly. CERN's Large Hadron Collider pushes even further. Protons race around the 27-kilometer ring At 99.999991% light speed, just 3 meters per second shy of light itself. At this velocity, the time dilation factor reaches 7,460. What we observe as a microsecond passes as just 134 nanoseconds for the proton. The LHC is essentially a time machine, showing us how physics works when time nearly stops. But the LHC reveals something even more profound. Despite humanity's most powerful machines and energies that recreate conditions from the first microseconds after the Big Bang, we cannot push particles those final 3 meters per second to true light speed. Each additional decimal place of precision towards c requires exponentially more energy. The universe's speed limit isn't just a suggestion, it's an absolute barrier that becomes infinitely strong as we approach it. Cosmic ray observations provide natural experiments at energies beyond any accelerator. The Pierre Auger Observatory in Argentina detects particles with energies exceeding 10 to the 20 electron volts. The oh my god particles. These cosmic bullets travel so close to light speed that crossing our galaxy takes mere seconds from their perspective. Yet precise timing measurements show they still fall short of true light speed, still experiencing some passage of time. The GZK cutoff provides a cosmic confirmation of extreme time dilation. Ultra-high energy protons interact with cosmic microwave background photons, losing energy through pion production. This creates a maximum distance from which we can detect the highest energy cosmic rays, about 100 million light-years. From the proton's perspective, the CMB is blue-shifted to gamma-ray energies, creating an impenetrable barrier. This cosmic speed trap confirms our understanding of how time dilation affects particle interactions. Pulsar observations offer another window into relativistic time. The double pulsar system PSR J07373039 consists of 2 neutron stars orbiting each other every 2.4 hours. Their orbital velocity reaches 1 million kilometers per hour, significant enough for measurable time dilation. The pulsars act as precise clocks, and their signals show exactly the time dilation Einstein predicted. After 20 years of observations, the match between theory and measurement is better than 1 part in 10,000. Gamma-ray bursts provide the most extreme astrophysical tests. These cosmic explosions accelerate particles to Lorentz factors exceeding 1,000. Time dilation so extreme that 1 second in the particle frame equals over 15 minutes in hours. The afterglow evolution of gamma-ray bursts follows precise patterns predicted by special relativity, confirming our understanding even in these most violent events. The cosmic microwave background itself demonstrates time dilation on the largest scales. This ancient light has been traveling for 13.8 billion years, redshifted from brilliant white to invisible microwaves. But the CMB also shows us the universe when time itself was different. In the early universe, the density of energy affected the rate of cosmic expansion, and thus the flow of time itself on cosmic scales. Gravitational wave observations add a new dimension to testing extreme physics. When LIGO detected merging black holes, the final orbits involved velocities exceeding half-light speed. The gravitational waves encoded information about time dilation in the strong field regime, where special and general relativistic effects combine. Every merger has matched predictions, confirming our understanding of time near the ultimate limit. Laboratory experiments with stored ions push precision to new extremes. At the GSI Helmholtz Center in Germany, lithium ions accelerated to 34% light speed show time dilation in their electron transitions. Spectral lines are shifted exactly as relativity predicts. These experiments can measure time dilation to parts per billion, finding perfect agreement with theory. The global positioning system provides an everyday confirmation that most people don't realize. GPS satellites orbit at 14,000 kilometers per hour, experiencing time dilation of about 7 microseconds per day. This seems tiny, but GPS requires nanosecond precision. Without relativistic corrections, GPS errors would accumulate at 11 kilometers per day. Every time your phone finds your location, it's confirming that time really does slow with motion. Atomic clock experiments have become extraordinarily sophisticated. In 2010, researchers at NIST compared optical atomic clocks at different heights, measuring gravitational time dilation from just 33 centimeters of elevation difference. While this is gravitational rather than motional time dilation, it demonstrates our ability to measure time's flow with 18-digit precision, accurate enough to detect walking speed velocities if applied to motion. The Ives-Stilwell experiment, first performed in 1938 and refined many times since, directly measures time dilation through the transverse Doppler effect. When atoms move perpendicular to the line of sight, classical physics predicts no frequency shift, but relativity predicts a redshift due to time dilation. Modern versions achieve precision of parts per billion, always confirming Einstein's predictions. Modern storage rings provide controlled tests of time dilation. At Brookhaven's G2 experiment, Morn circled a magnetic storage ring at 99.94% light speed. Their lifetime dilated by a factor of 29.3, exactly as predicted. The experiment also revealed subtle effects from Thomas precession, a relativistic correction to spinning particles in circular orbits. Space missions offer unique opportunities to test time dilation. The gravity probe. An experiment in 1976 carried a hydrogen maser clock on a rocket to 10,000 kilometers altitude. Comparing its frequency to ground clocks revealed both gravitational and motional time dilation, matching predictions to 70 parts per million. Future missions with improved clocks could test relativity to unprecedented precision. When we confront the reality that time stops at light speed, we're forced to grapple with questions that transcend physics and enter the realm of philosophy. What does existence mean without duration? Can something be conscious without experiencing time? These aren't idle speculations, they're fundamental questions about the nature of reality that arise directly from Einstein's equations and challenge our deepest assumptions about consciousness, identity, and existence itself. The block universe interpretation of relativity suggests that past, present, and future all exist simultaneously in four-dimensional spacetime. From this perspective, time doesn't flow. We simply experience successive slices of an eternal, unchanging whole. Photons experiencing no time might see this eternal structure directly. They exist outside the illusion of temporal flow that constrains massive beings like us. This raises profound questions about free will. If the future already exists in the block universe, are our choices predetermined? The light-speed perspective suggests a cosmos where everything that will happen has, in some sense, already happened. Yet quantum mechanics introduces uncertainty that might preserve some form of agency. The intersection of relativistic determinism and quantum indeterminacy remains one of philosophy's deepest puzzles. Consider what consciousness means at light speed. Our awareness seems intrinsically temporal. Thoughts flow, memories form, experiences unfold. William James called consciousness a stream, emphasizing its temporal nature. But if time stops at light speed, could consciousness exist? This isn't just about photons, it's about whether awareness itself requires duration or if some form of timeless consciousness is possible. The anthropic principle takes on new meaning in this context. We exist as massive, time-experiencing beings because that's the only way consciousness as we know it can emerge. The universe's light-speed limit isn't a restriction, but a necessity for temporal beings like us to exist. Without this cosmic speed limit, causality would break down, making stable structures and evolution impossible. Eastern philosophies have long spoken of timeless states of consciousness, the eternal now of meditation, the dissolution of temporal awareness in mystical experiences. While these are subjective experiences within time, rather than truly timeless states, they hint at modes of awareness that transcend ordinary temporal flow. The physics of light speed gives unexpected support to these ancient insights about time's malleable nature. The ship of Theseus paradox becomes extreme at relativistic speeds. If you travel near light speed, your atoms remain the same, while Earth's atoms are replaced multiple times through metabolism and repair. Which you is more continuous? The one whose atoms are preserved by time dilation, or the one whose patterns persist through atomic replacement? Identity itself becomes problematic when time flows at different rates. Death and immortality take on new meanings near light speed. A traveler approaching light speed arbitrarily closely could outlive the stars, watching the universe's entire future history unfold in what feels like a human lifetime. This isn't immortality in the traditional sense. The traveler still ages and dies in their own reference frame, but it's a kind of temporal transcendence, experiencing eons of cosmic time. The simulation hypothesis gains an interesting twist from light-speed physics. If our universe is simulated, the light-speed limit might be a computational constraint, a maximum rate at which the simulation can process information. Photons experiencing no time might exist at the simulation's boundary conditions, where the normal rules of temporal computation don't apply. Consciousness might be more fundamental than we assume. Some interpretations of quantum mechanics require conscious observers to collapse wave functions. If consciousness plays a fundamental role in physics, what happens at light speed, where normal observation seems impossible? This connects to debates about panpsychism, whether consciousness is a basic feature of reality rather than an emergent property. The hard problem of consciousness, explaining how subjective experience arises from objective physics, becomes even harder at light speed. How can there be something it is like to be a photon if photons experience no time? Either photons have no subjective experience, suggesting consciousness requires time, or they have some timeless form of experience we can't comprehend. Information theory provides another angle. Claude Shannon showed that information is physical, requiring energy and obeying thermodynamic laws. But information processing seems to require time. Computation involves state changes over duration. At light speed, where time stops, can information exist without being processed? This touches on whether information or computation is more fundamental to reality. The many worlds interpretation of quantum mechanics suggests that reality branches into parallel universes at every quantum event. From a photon's timeless perspective, would all these branches be experienced simultaneously? This could imply a form of cosmic consciousness that transcends individual timeline, experiencing all possible histories at once. Personal identity relies on temporal continuity. We are our memories, our ongoing stream of experiences. But at light speed, with no time for new experiences or memories to form, what remains of identity? This suggests that consciousness as we understand it is fundamentally incompatible with light-speed travel, explaining why the universe restricts massive beings to subluminal velocities. The measurement problem in quantum mechanics might relate to time's role in consciousness. Wave function collapse seems to require a temporal process, a transition from superposition to definite state. At light speed, with no time for collapse, would quantum systems remain perpetually uncollapsed? This hints at deep connections between time, measurement, and the emergence of classical reality from quantum substrates. Some physicists propose that time itself might be emergent rather than fundamental. In this view, timeless quantum entanglement networks give rise to the appearance of temporal flow for embedded observers. Photons existing at light speed might inhabit this more fundamental timeless layer from which time emerges for slower entities. The question of whether mathematics is discovered or invented takes on new significance. The mathematical laws governing time dilation exist independently of human minds, yet they describe something, time, that might only exist for conscious observers. This suggests a deep connection between consciousness, mathematics, and the structure of reality that light-speed physics helps illuminate. Near-death experiences often involve reports of time dilation or timelessness, reviews happening in instants, expanded awareness of past and future. While these are likely neurological phenomena rather than genuine time dilation, they suggest that human consciousness can experience altered temporal states that hint at what timeless awareness might feel like. As we stand at the frontier of our understanding about time at light speed, new experiments and theories promise to push our knowledge even further. The next decades will bring revolutionary instruments and insights that could transform our understanding of time's ultimate limits. From quantum gravity theories that might modify relativity at extreme scales, to experiments that probe the intersection of quantum mechanics and time dilation, we're entering an era where century-old questions might finally find answers. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will detect gravitational waves from merging supermassive black holes. These cosmic collisions involve event horizons where time dilation becomes infinite, potentially revealing new physics at the boundary between time and timelessness. LISA's sensitivity will allow us to map spacetime geometry near the ultimate limit where time stops. Quantum gravity theories suggest that spacetime itself might break down at the Planck scale, distances of 10 to the negative 35 meters and times of 10 to the negative 43 seconds. At these scales, the smooth time dilation of Einstein's relativity might become granular. Loop quantum gravity predicts discrete jumps in time rather than continuous flow. If confirmed, this would mean that approaching light speed involves stepping through discrete time states rather than smooth deceleration. The Event Horizon Telescope, which captured the first image of a black hole in 2019, continues to improve its resolution. Future observations might detect effects of extreme time dilation near event horizons, places where time nearly stops from our perspective. Watching matter spiral into black holes in real time could reveal how physics behaves when time approaches zero. Quantum clock interferometry represents a new frontier. By putting quantum clocks in superposition of different velocities, physicists hope to observe quantum superpositions of different time dilations. This would probe whether time dilation obeys quantum mechanics, or if there's a fundamental conflict between quantum theory and relativity at extreme speeds. The proposed Atomic Clock Ensemble in Space, ACES, will place ultra-precise atomic clocks on the International Space Station. Comparing these to ground clocks will test time dilation with unprecedented precision, potentially revealing tiny deviations from Einstein's predictions that could point toward new physics. Even parts per quintillion differences could indicate quantum corrections to relativity. Neutrino telescopes like IceCube are detecting particles with energies that push against theoretical limits. Some models suggest that quantum gravity effects might allow particles to slightly exceed light speed at extreme energies. While no such violations have been confirmed, each new high-energy neutrino tests the absolute nature of the cosmic speed limit. The search for Lorentz invariance violation continues with ever greater sensitivity. Some quantum gravity theories predict tiny variations in light speed depending on photon energy. Observations of gamma-ray bursts across billions of light-years could reveal if high-energy photons travel slightly faster or slower than low-energy ones. So far, light speed appears perfectly constant, but future observations might find surprises. Quantum entanglement experiments are pushing toward macroscopic scales. If large objects can be entangled, we might observe how time dilation affects quantum correlations in ways current theory doesn't predict. This could reveal whether the timeless correlations of entanglement conflict with relativistic time dilation at observable scales. The holographic principle suggests that our three-dimensional reality might be encoded on a two-dimensional surface. If true, time itself might be emergent from more fundamental timeless physics. Future experiments might detect the pixels of holographic spacetime, revealing that smooth time dilation is actually discrete at the smallest scales. Metamaterials with exotic optical properties allow us to simulate cosmic phenomena in the laboratory. Researchers have created materials where light effectively travels faster than C, though information still can't exceed light speed. These superluminal materials might reveal new aspects of how time and causality relate when normal speed limits are circumvented. Time crystals, structures that repeat in time rather than space, challenge our understanding of temporal physics. Future experiments might create relativistic time crystals that combine periodic time behavior with extreme time dilation. This could reveal whether time's fundamental nature changes at relativistic speeds. The quantum Zeno effect shows that frequent measurement can freeze quantum evolution. New proposals suggest using this effect to create temporal shields that protect quantum states from decoherence by effectively slowing their internal time. This might lead to quantum computers that operate in dilated time, processing information in ways that classical physics forbids. Cosmological observations continue to constrain how time behaves on the largest scales. The Dark Energy Survey and upcoming Vera Rubin Observatory will map billions of galaxies, potentially revealing whether time itself evolves cosmologically. If the flow of time has changed over cosmic history, it might affect how we understand time dilation. Artificial intelligence might provide new insights into timeless physics. AI systems don't experience time the way biological consciousness does. As AI becomes more sophisticated, it might offer perspectives on what timeless information processing could mean, potentially illuminating the photon's eye view of reality. The intersection of thermodynamics and time dilation remains poorly understood. How does entropy change from different reference frames? Can time dilation affect the arrow of time? Future experiments with quantum heat engines operating at relativistic speeds might reveal surprising connections between time, energy, and information. String theory predicts extra dimensions that might modify time dilation at extremely high energies. While these effects would be tiny, future particle accelerators or cosmic ray observations might detect signatures of extra dimensions through modified dispersion relations, variations in how particles of different energies experience time dilation. The multiverse hypothesis suggests our universe might be one of many with different physical laws. Some universes might have different speed limits or no speed limit at all. While seemingly untestable, future observations of cosmic boundaries or anomalies might reveal influences from other universes with different temporal physics. Quantum biology is revealing that living systems exploit quantum effects like entanglement and tunneling. As we understand more about how life uses quantum physics, we might discover that organisms have evolved mechanisms that interact with time in unexpected ways, possibly providing new perspectives on consciousness and temporal experience. The ultimate question remains, is the light speed limit truly absolute, or might there be loopholes we haven't discovered? While every experiment confirms Einstein's speed limit, science progresses by questioning even its most established principles. The future might reveal that time's behavior at light speed is even stranger than we currently imagine. Throughout the universe, countless natural phenomena demonstrate the intimate relationship between light speed and time's flow. From the dance of binary pulsars to the jets of quasars, from the collision of galaxies to the quantum vacuum itself, nature provides an endless laboratory where time pushes against its ultimate limits. These cosmic experiments don't just confirm our theories, they reveal new layers of mystery about what happens when time approaches zero. In the center of our galaxy, stars orbit the supermassive black hole, Sagittarius A, at velocities exceeding 5,000 kilometers per second. The star S2, tracked for over 20 years, swings by the black hole at 3% of light speed. During its closest approach, S2 experiences time dilation of about 5%, meaning time passes measurably slower for the star than for us watching from Earth. This isn't theory, it's directly observed through the gravitational redshift of the star's light. The gravity instrument on the Very Large Telescope has measured this time dilation with exquisite precision. As S2 plunges toward the black hole, its spectral lines shift exactly as Einstein predicted. We're literally watching time slow down from 26,000 light-years away. Future observations of stars passing even closer to the black hole will probe time dilation in ever-stronger gravitational fields. Quasar jets provide another cosmic laboratory. These streams of plasma shoot from supermassive black holes at 99% light speed or higher. In the quasar 3C279, knots of material appear to move at 7 times light speed across the sky, an illusion created by time dilation and projection effects. The material is actually moving at about 99.8% light speed at a small angle to our line of sight. These jets maintain coherence over millions of light-years despite their extreme velocities. From our perspective, particles in the jet age incredibly slowly, allowing unstable particles to travel vast distances. From the jet's perspective, the universe is length contracted, making intergalactic journeys seem much shorter. It's a cosmic demonstration of how approaching light speed warps both space and time. Binary millisecond pulsars showcase time dilation with clockwork precision. PSR J19093744 spins 339 times per second while orbiting a white dwarf companion. The system acts like a cosmic clock shop with multiple timekeepers moving at different velocities. Pulsar timing arrays have measured how orbital motion affects each clock, confirming relativistic time dilation to better than 1 part in a million. The cosmic web itself, the largest structure in the universe, reveals how time and motion interweave on the grandest scales. Galaxy clusters move along cosmic filaments at hundreds of kilometers per second. While these velocities are small compared to light speed, the sheer scale means that time flows at slightly different rates in different parts of the cosmic web. Over billions of years, these tiny differences accumulate, affecting how structures evolve. Fast radio bursts add new mysteries to our understanding. These millisecond flashes of radio waves come from distant galaxies, some repeating unpredictably. The burst durations are so short that the emitting regions must be smaller than light travel distances, perhaps just kilometers across. Whatever creates these bursts involves matter moving at extreme velocities where time dilation becomes significant. The merger of galaxy clusters creates shock waves where particles are accelerated to near light speed. The bullet cluster collision accelerated electrons to 99% light speed or higher, creating synchrotron radiation we observe as radio halos. These cosmic particle accelerators achieve energies far beyond any human-made device, pushing matter into regimes where time nearly stops. Blazars, quasars with jets pointed directly at Earth, show extreme relativistic beaming. Their brightness varies on timescales of hours or days, impossibly fast for objects that span light years. Time dilation explains this. Variations that take years in the jet's frame appear compressed to days in hours due to the jet's near-light velocity toward us. We're seeing cosmic processes in fast forward. The quantum vacuum itself dances with time dilation. Virtual particle pairs constantly appear and annihilate, borrowing energy from the vacuum for times shorter than Heisenberg's uncertainty principle allows. Near the light speed limit, these quantum fluctuations experience time dilation. Some theories suggest this creates a kind of quantum friction that enforces the cosmic speed limit. Cosmic strings, if they exist, would be one-dimensional defects in space-time moving at near light speed. These hypothetical objects would create gravitational lenses with unique signatures, double images with no distortion. The detection of cosmic strings would reveal how one-dimensional objects experience time at relativistic velocities, potentially confirming or challenging our understanding of time dilation. Primordial black holes formed in the early universe might be evaporating through Hawking radiation right now. As they shrink, their temperature increases, accelerating the evaporation. In their final moments, these black holes would release particles at energies where time dilation becomes extreme. Detecting such an evaporation would probe physics at the intersection of quantum mechanics, gravity, and time. The cosmic neutrino background, relic neutrinos from the Big Bang, fills space with particles moving at nearly light speed. These ancient neutrinos have been traveling since the universe was 1 second old, experiencing extreme time dilation throughout cosmic history. When we eventually detect them directly, we'll be observing particles for which billions of years have passed like moments. Magnetars, neutron stars with extreme magnetic fields, accelerate particles along field lines to near light speed. The magnetic field strength can exceed 10 to the 15 Gauss, creating conditions where quantum electrodynamics predicts vacuum birefringence and photon splitting. These exotic environments probe how electromagnetic fields behave when particles approach the speed of light. Active galactic nuclei show coordinated variations across vast distances. In some cases, different parts of the accretion disk brighten in sequence, as if a signal is propagating faster than light. The explanation involves time dilation and light travel delays combining to create apparent superluminal coordination. These cosmic illusions teach us how time and causality interweave at extreme velocities. The universe's expansion adds another layer to cosmic time dilation. Distant galaxies recede from us at significant fractions of light speed due to cosmic expansion. Their time appears to run slow from our perspective. Supernovae in distant galaxies evolve in slow motion. This cosmological time dilation is distinct from special relativistic effects, showing how space itself can affect time's flow. Gamma-ray bursts accelerate particles to Lorentz factors exceeding 1,000. At these extremes, a particle's lifetime is extended by the same factor. Pions that would decay in nanoseconds survive for microseconds. Muons that live microseconds persist for milliseconds. The universe becomes a strange place where unstable particles achieve a kind of temporal immortality through sheer velocity. As we reach the end of our journey exploring what happens to time at light speed, we arrive at perhaps the most profound realization of all. The universe has embedded within its very fabric a fundamental divide between the temporal and the timeless. We massive beings live in the temporal realm, experiencing the flow of moments, accumulating memories, anticipating futures. But light itself inhabits an eternal now, a timeless state that connects every point in space and moment in time into a singular, unchanging whole. This isn't just poetry, it's the literal truth encoded in Einstein's equations. Every photon that has ever existed or will ever exist experiences its entire journey, whether across a room or across the universe, in zero time. The sunlight warming your face left the sun's surface 8 minutes ago from your perspective, but from the photon's view, departure and arrival are one event. The cosmic microwave background radiation, traveling for 13.8 billion years to reach us, experiences its entire journey instantaneously. In the realm of light, all of cosmic history collapses into a single, eternal moment. This timeless perspective reveals something extraordinary about our universe. Every point in space is connected to every other point through light's timeless journey. When you see a star, you're not just receiving old information. You're participating in a connection that, from light's perspective, is instantaneous across any distance. The universe isn't just connected by light, it's unified by it in a timeless web that transcends our temporal experience. Consider what this means for causality itself. We think of cause and effect as separated by time, but light connects causes to effects instantaneously from its own perspective. A star exploding billions of years ago and you seeing it tonight are, for the light involved, the same event. The universe's causal structure isn't just about temporal sequences, it's about timeless connections that we temporal beings perceive as unfolding through time. The photons from distant galaxies that enter our telescopes have witnessed, if we can use that word, for something experiencing no time, the entire history of cosmic expansion in zero duration. They carry information not through time, but despite time, maintaining connections across a universe that has expanded enormously during what we perceive as their journey. Every observation we make depends on these timeless messengers. But here's the beautiful paradox. We temporal beings are made possible by the very speed limit that prevents us from ever achieving timelessness. If massive objects could reach light speed, causality would break down, effects could precede causes, the stable structures of atoms, molecules, DNA, and consciousness could never form. The universe's speed limit isn't a restriction, it's the foundation that allows complexity, life, and awareness to exist. Your consciousness is a fundamentally temporal phenomenon. Every thought requires neurons firing in sequence. Every memory involves encoding experiences over time. Every decision involves projecting into possible futures. The speed of light limit ensures that these processes can unfold in meaningful sequences, that causes can lead to effects, that experiences can accumulate into wisdom. Yet you're also connected to the timeless realm. The electromagnetic forces holding your atoms together are mediated by virtual photons, timeless quantum messengers. The light entering your eyes connects you instantaneously, from light's perspective, to everything you see. You exist at the intersection of the temporal and timeless, a bridge between two fundamentally different modes of existence. This duality extends throughout nature. Every atom is a dance between temporal electrons and timeless photons. Every chemical reaction involves massive particles moving through time while exchanging timeless force carriers. Every star shines by converting temporal matter into timeless light. The universe itself is a vast interplay between things that experience time and things that don't. Modern physics hints that this division might be even more fundamental than we realize. Some theories suggest time itself is emergent, that the timeless quantum realm is more basic, and time only appears for certain observers under certain conditions. We might be temporal islands in a fundamentally timeless reality, experiencing an illusion of flow in what is actually an eternal, unchanging whole. The implications for human existence are profound. We age and die in time, but the light we emit, the infrared radiation from our warm bodies, the radio waves from our technology, the reflections of sunlight from our faces, enters the timeless realm. In a sense, every moment of our existence is preserved in the light that carries it into space, frozen in an eternal now that will outlast the stars. When you look at the night sky, you're seeing the universe's history laid out in space. But from light's perspective, all that history exists simultaneously. The Big Bang, the formation of galaxies, the birth of stars, the emergence of life, and the distant future when the last stars die, all coexist in the timeless realm of light. We temporal beings see slices of this eternal whole, experiencing it as a story unfolding through time. The search for meaning takes on new dimensions when we understand time's limits. We cannot achieve timelessness ourselves, but we participate in it every time we see or are seen. We're temporary patterns in a universe where time and timelessness interweave. Our brief temporal existence gains significance not despite its brevity, but because of it. We're the universe's way of experiencing time, just as light might be its way of transcending it. Science itself is our attempt to understand both realms. Through mathematics and observation, we temporal beings have discovered the timeless laws that govern reality. Equations like E equals mc squared are timeless truths that we discovered at particular moments in time. We use our temporal consciousness to reach toward eternal principles, building bridges of understanding between the flowing and the fixed. As technology advances, we edge closer to light speed in our experiments, probing the boundary between time and timelessness. Each particle we accelerate towards C, each photon we detect from distant galaxies, each gravitational wave we observe from merging black holes teaches us more about this fundamental divide. We may never cross it ourselves, but we can approach it asymptotically, learning ever more about what lies on both sides. The question, does time stop at light speed, has led us on a journey through the deepest mysteries of physics and philosophy. The answer is both yes and no. Yes, time stops for anything traveling at exactly light speed, but no massive object can ever reach that speed to experience it. This isn't a limitation, but a feature of the universe that makes our existence possible. We are beings of time, made from stardust, contemplating our place in a cosmos where time and timelessness coexist. Every atom in your body has experienced billions of years, yet the light reflecting from your eyes experiences no time at all. You are simultaneously ancient and instantaneous, temporal and connected to the timeless, finite yet touching the infinite. As you go forward from this moment, remember that you exist at the intersection of two realms. You experience time's flow while being built from timeless laws. You age and change while participating in eternal patterns. You're separated from light's timeless perspective by an unbridgeable gap, yet connected to it every time you open your eyes. This is the profound gift of being human, to experience time while knowing about timelessness, to be finite while comprehending the infinite, to be mortal while touching the eternal through understanding. The universe has arranged itself so that conscious beings like us must experience time to exist, while light, the very thing that allows us to see and know the cosmos, transcends time entirely. In this cosmic arrangement, we find not limitation, but profound meaning. We are time's children, light's observers, and the universe's way of experiencing both the temporal and the eternal. And in understanding what happens when time stops at light speed, we discover not just physics but poetry, not just equations but existence itself. If you made this far, make sure to give a thumbs up and subscribe to the channel. And if you enjoyed this video, I am sure you will love this one at the left side of the screen. What if we could travel faster than light? In this video, discover the mind-blowing science and consequences of breaking the cosmic speed limit. Explore how faster-than-light travel would transform space exploration, time, the future of humanity, and much more. See you there.